Saudi Arabia is the world's largest producer of desalinated water, where researchers have patented several technologies to extract minerals from water.
Saudi Arabia does something every single day that should not be possible. It takes water from the sea, strips out the salt, and then forces that water hundreds of kilometers across one of the hottest, driest deserts on Earth. There are no rivers helping it along, no steady rainfall backing it up, and no gravity doing the work.
Water out of the ground that belongs to the state of Arizona, and essentially it's being exported to Saudi Arabia.
Instead, steel, pressure, and constant energy keep the water moving. And if that system ever slows down, entire cities feel it, almost immediately.
After the water goes through its original cleaning, it gets pumped up here into this pool.
So let's start with why this country had no choice but to build an invisible river, and how it manages to keep water flowing where nature never intended it to go. Living without rivers or rain. Imagine living in a place where the sun feels relentless, where months can pass without real rain, and where most of the land you see is sand or rock. How does a country like that even function day to day? We're talking about a region where extreme heat and very low rainfall make natural fresh water scarce and unreliable. In much of Saudi Arabia, average rainfall is so low that it can't refill rivers or lakes in any meaningful way, and the heat causes whatever little moisture exists to evaporate quickly. There simply isn't a steady, natural water system that people can depend on year after year. Now here's a question worth asking right away. If water is so limited, why isn't the population small and spread out? The reality is that Saudi Arabia has tens of millions of people, and that number has grown alongside modern cities, industries, and daily expectations of comfort. People still need clean water to drink, cook, shower, and wash clothes. Schools, hospitals, and homes all depend on water every single day. On top of that, industries need water to cool machines, clean equipment, and keep production moving. Even power plants rely on water to function properly. So while nature provides very little, demand keeps rising. Water use doesn't slow down just because the land is dry, and it doesn't pause during heat waves or long summers. You might wonder, couldn't they just drill more wells and pump water from underground? That seems like the obvious solution, but it only works up to a point. Groundwater in desert regions is often old water that fell as rain thousands of years ago. Once it's pumped out, it doesn't quickly come back. Over time, wells can dry up, and water levels drop deeper and deeper, which makes pumping more expensive and less practical. There's another problem too. When groundwater is taken out faster than it can be replaced, salty seawater can slowly creep into underground aquifers near the coast. This process makes the remaining water salty and unsafe to drink or use on crops. So drilling more wells may help for a while, but it's not a reliable long-term answer for a country this large. So, even if water exists somewhere, how do you get it to where people actually live? Distance plays a huge role in this story. Much of Saudi Arabia's population lives inland, far from any natural freshwater source. At the same time, the most reliable and abundant water source, the sea, sits along the coast. That creates a serious mismatch. Water is needed in cities, towns, farms, and industrial zones that may be hundreds of kilometers away from the shoreline. Moving water that far across desert terrain isn't easy. Pipes must survive intense heat, shifting sand, and constant pressure, all while operating day and night without failure. This is where the situation turns from difficult to critical. In many parts of the world, water shortages are treated as emergencies that happen once in a while. In Saudi Arabia, scarcity is the normal condition. Water isn't something people hope will be available tomorrow. It has to be guaranteed. Without a steady supply, daily life becomes unstable very quickly. Hospitals can't function safely, sanitation systems fail, and cities grind to a halt. So water here is basically keeping society running. Think about that for a moment. Every glass of water someone drinks, every shower taken, every hospital room cleaned depends on a system that has to work perfectly in a place where nature offers very little help. There's no dependable river flowing downhill to do the work. There's no rainy season that refills reservoirs year after year. Instead, water must be created, controlled, and delivered on purpose. So how do you solve a problem like this? You stop waiting for nature to cooperate, and you build something that replaces what nature doesn't provide. That's the big idea behind Saudi Arabia's water system. Instead of relying on rainfall or rivers, the country turns to the sea. Seawater is nearly endless and always available, but it comes with one major problem. It's full of salt. Salt makes water undrinkable and useless for most farming and industrial needs.
The highly salty wastewater, known as brine, flows back into the sea, and that can affect marine ecosystems.
Removing that salt takes energy, advanced technology, and careful control at every step. Once the salt is removed, the challenge isn't over. Clean water still has to be pushed inland across harsh desert landscapes. That means forcing water through long steel pipelines, using pumps to keep it moving, and constantly monitoring pressure, temperature, and flow. This is a non-stop process that runs every hour of every day. If it stops, even briefly, the effects are felt immediately. But what happens if this system fails? Cities run dry. Hospitals lose a critical resource. Industries shut down. Life becomes unstable very fast. That's why water in Saudi Arabia is treated as a national lifeline. Where rivers don't exist, steel pipelines take their place. Where rain doesn't fall, desalination plants step in. Where water can't move on its own, powerful pumps force it forward. This system exists because it has to. It's built so that daily life can continue in a place where nature sets very hard limits. Understanding this problem is the key to understanding everything that follows. Before we talk about desalination plants, giant pipelines, and complex machinery, it's important to see why they exist at all. In Saudi Arabia, water is something you make, move, and protect every single day. Turning the sea into drinking water. So if there are no rivers to rely on, where does the water actually begin its journey? It all starts at the coast, out in the open sea, where seawater becomes the raw material for everything that follows. Instead of scooping up water near the shore, long intake pipes stretch hundreds of meters offshore into deeper, calmer water. This is done on purpose, because water closer to land carries more sand, trash, and stirred up sediment. At the very mouth of these pipes, large intake screens act like guards at the door, blocking seaweed, plastic, and marine life, so fish, crabs, and jellyfish don't get pulled inside. This may sound basic, but if living creatures or debris slip through, they can damage equipment and shut down the entire plant. Here's a question that clears up a big misconception. Can you just take seawater and remove the salt right away? Not really, and skipping this step would be a disaster. Before salt is even addressed, seawater has to be cleaned of dirt you can see, and particles so tiny they're invisible to the naked eye. This stage is called pre-treatment, and it quietly does a lot of the heavy lifting. The water flows through large tanks filled with layers of sand and other filtering material. As it moves downward, sand, silt, and suspended particles get trapped between the grains. At the same time, small doses of chemicals are added to help tiny particles stick together and sink instead of floating through the system. This protects what comes next, because the membranes used later are delicate and expensive, and once they clog or tear, repairs are slow and costly. So what actually removes the salt? This is where reverse osmosis comes in, and it's easier to understand than it sounds. Salt doesn't dissolve loosely in water. Instead, it binds tightly to water molecules. To separate them,
But there's an entire ecosystem here of fish that manage somehow to sneak in.
brute force is needed. Extremely powerful pumps push the pre-treated seawater against ultra-fine membranes under very high pressure. These membranes are engineered with openings so small that water molecules can squeeze through, but salt and other impurities cannot. The salt stays behind, and the fresh water passes through to the other side. The pressure involved here is intense, many times greater than normal air pressure, and maintaining it requires constant energy and careful control. Now here's something people don't always realize. One round of reverse osmosis can already produce very clean water, but for drinking water standards, especially at national scale, that's often not enough. Tiny leftover ions and dissolved substances can still remain. That's why many plants send the water through a second purification stage. This second pass uses even finer membranes or adjusted pressure to remove what little remains. By the time the water leaves this stage, it's extremely pure, almost stripped down to its basic chemical form. That leads to another problem that sounds strange at first. Water that pure isn't ideal to drink. It lacks minerals, tastes flat, and can even be slightly aggressive to pipes and storage systems. So the next step is to carefully put some things back in. During remineralization, controlled amounts of minerals like calcium and magnesium are added, and the pH is adjusted to a safe, balanced range. This makes the water taste more natural, protects infrastructure, and ensures it's healthy for long-term use. It's a quiet step, but without it, the final product wouldn't be suitable for everyday life. Now let's talk about the part that often decides whether desalination is affordable or painfully expensive: energy. Reverse osmosis depends on massive pumps that run non-stop, and those pumps consume enormous amounts of electricity. Every liter of water pushed through the membranes represents energy spent overcoming pressure and resistance. This is why modern desalination plants focus so much on efficiency. Many systems now use pressure or energy recovery devices that capture leftover pressure from the salty brine stream and feed it back into the system. These devices don't remove the energy cost, but they significantly reduce it. Without them, the price of each cubic meter of water would climb fast, making large-scale desalination far harder to sustain. That brings up another important question. What happens to the salt that gets removed? It doesn't vanish. What's left behind after desalination is a concentrated brine, much saltier than the original seawater, along with traces of treatment chemicals. This brine has to be handled carefully. In coastal plants, it's usually released back into the sea through specially designed outfalls that help it mix and dilute quickly. If discharged improperly, it can raise local salinity levels and put stress on marine life. Managing this waste stream is a constant balancing act between keeping the system running and protecting the surrounding environment. When you step back and look at the full process, desalination starts to feel less like a single machine and more like a carefully choreographed system. Intake structures protect the plant from physical damage. Pre-treatment keeps membranes alive and efficient. Reverse osmosis does the hard work of separating salt from water. Secondary purification improves quality. Remineralization makes the water usable. Energy recovery keeps costs under control. Brine management reduces environmental impact. Every part depends on the others, and if one link weakens, the whole system feels it. Here's a question that really puts things into perspective. What happens if this system stops, even briefly? Well, it's immediate disruption. Water production slows or halts, pressure drops, and downstream users feel the effects quickly. That's why desalination plants operate around the clock, with teams monitoring pressure, flow rates, membrane health, energy use, and water quality in real time. There's no natural backup waiting to take over if something goes wrong. So when fresh water finally leaves the plant, ready to begin its journey inland, it exists because the machines kept running, the system stayed balanced, and people stayed alert. And this is only the first half of the story, because once that water is created, it still has to cross hundreds of kilometers of desert before it ever reaches a home. A river built from steel. How do you move enormous volumes of water across hundreds of kilometers of open desert without losing pressure, damaging the system, or watching it slowly fall apart under heat and sand? Well, you create an underground river, not of rock or soil, but of steel. We're talking about pipelines built to survive conditions that would destroy most everyday materials. Steel is chosen because it can handle very high pressure, repeated heating and cooling every single day, and decades of non-stop use. Plastic pipes would soften or crack under this stress, and concrete would struggle with pressure and long-term fatigue. But steel can bend slightly without failing and hold its strength over time. So how are these pipes actually made? It starts in factories where thick steel plates arrive as flat sheets. These plates are cut to precise sizes, then slowly rolled by heavy machines until they curl into a perfect cylinder. Once the edges meet, they are welded together along a long seam, forming a solid pipe. After welding, the pipe is cooled to stabilize the metal and prevent weak spots from forming. The ends are then shaped with beveled edges, which might sound minor, but this detail is critical because it allows two pipe sections to fit together cleanly and be welded without gaps. Finally, protective coatings are applied to the inside and outside surfaces, creating a barrier between the steel and the harsh environment it's about to face. You might ask, if steel is already strong, why does it need so much extra protection? Think of corrosion like rust, slowly eating away at a car left out in bad weather. Buried steel faces, heat, moisture, salt and oxygen all at once, which is a perfect recipe for damage over time. To fight this, pipelines use multiple defenses. Thick coatings act like armor, keeping harmful elements away from the metal. Cathodic protection adds another layer, using controlled electrical currents or sacrificial metals that corrode first so the pipe doesn't have to. On top of that, regular inspections act like medical checkups, catching small issues before they turn into serious problems. Without this combination, even the strongest pipe would fail far sooner than planned. Before any pipe touches the ground, engineers have to decide exactly where it should go. A desert may look empty and flat, but it's more like a shifting mattress than a solid floor. Some areas have loose sand that moves with the wind, while others hide weak soil that can collapse when disturbed. Survey teams study maps, satellite images, and ground samples to find stable paths, avoiding erosion zones and flood-prone channels that appear during rare storms. Choosing the wrong route would be like building a road on melting ice. It might look fine at first, but cracks and damage would follow. Now imagine the construction phase. Trenches are dug along the planned route, often stretching as far as the eye can see. These trenches aren't random ditches. They're cut to precise depth and width, so the pipe sits evenly and doesn't rest on sharp rocks or uneven ground. Before the pipe is placed, a bedding layer of fine material, usually sand or screened soil, is spread along the bottom. This layer acts like a cushion, distributing the pipe's weight and reducing pressure points. Then, massive side boom tractors, which look like cranes on tank tracks, lift each pipe section and lower it slowly into the trench. Multiple machines work together, keeping the pipe level so it doesn't twist or scrape against the trench walls. This is where the process starts to resemble assembling a giant underground train track. Each pipe section must line up perfectly with the next. Alignment clamps hold the ends steady, while automated welding machines join them. These welds are treated like critical joints in an airplane, not trusted by sight alone. Ultrasonic inspections send sound waves through the metal, similar to how doctors use ultrasound to see inside the body. If a hidden flaw is found, it's fixed immediately. Once approved, the exposed joint is coated again, sealing it so the connection is just as protected as the rest of the pipe. After placement, the trench is filled back in carefully, layer by layer. This isn't just dumping dirt back on top. The first layer is soft material to protect the coating, followed by compacted soil to lock everything in place. Think of it like packing a fragile item in a box. If you don't cushion it properly, even small movements during shipping can cause damage. In the desert, heat and wind can slowly shift soil, so proper compaction prevents future sinking that could bend the pipe like a stressed beam.